Right.
Shall we start the session?
Yes. Hello, everyone. Welcome to the Topology Optimization webinar. Today is the 8th session, which is also the last session before the new year. It is not a good time for Professor Shinji Nishiwaki, but he kindly agreed and helped us organizing this session. Thank you very much, and thank you to all our speakers, and especially those from Asia. It's quite late. Thank you for joining us. And Professor Nishiwaki, please.
Well, thank you very much for giving us such a nice chance to give a talk. Actually, we have 5 presenters in this session, and each presenter has 15 minutes, including the question and the discussion. Okay, so first presenter is Professor Izui from Japan. The title of the paper is Isogeometric Topology Optimization of Anisotropic Metamaterials for Controlling High Frequency Electromagnetic Wave. Okay, let's get started. I'll give the floor to the Professor Izui. Please start.
Okay. Let me share the slide. Okay. Can you see the slide?
Yes.
Okay. Okay, thank you for the introduction, Professor Nishiwaki. Today's my talk is about the design of microstructure of anisotropic electromagnetic wave metamaterials. My name is Kazuhiro Izui, and this is the collaborative research between the Hope University and Kyoto University. And first, let me talk about the background of our research. As everybody here knows, topology optimization techniques are recently applied to a variety of products and devices. And our design target in this research is electromagnetic metamaterials. And Carlos and Ito said the electromagnetic metamaterial is artificial, effectively homogeneous magnetic structures with unusual properties not readily available in nature. For example, the structures having negative reflective index and negative permeability and permittivity, kinds of electromagnetic metamaterials. Such a type of materials can be used to greatly enhance the performance of many devices, as you know. And especially hyperbolic metamaterials have a very interesting wave propagation properties compared with conventional bulk structures. This kind of metamaterial can provide hyperbolic dispersion relationship of wave propagation, and such property can be used in the design of flat lanes and or hyperlanes, for examples. So the objective of this research is construct a topology optimization of the microstructure design of electromagnetic and hyperbolic metamaterials. We use the level set method in topology optimization, and also we use the isogeometric approaches in the numerical analysis. So to analyze such wave propagation phenomenon of multi-scale structures, a new analysis method for microstructures must be developed, since the conventional homogenization method cannot be used for high frequency wave propagation problems. In this research, the high frequency homogenization method for electromagnetic wave is introduced. The basic concept of such high frequency homogenization method was developed by Cluster et al. In 2010. In this technique, And in our application, the governing equation is a Helmholtz equation, and this is the governing equation. And in high frequency homogeneous method, asymptotic expansion is applied not only to the magnetic field H, but also to frequency value omega. By using this technique, we can obtain the homogenized wave equation as shown here. And in this equation, Tij is so-called homogenized material tensor. And this tensor characterizes the property of wave propagation phenomenon of macroscopic structure. This slide shows the relationship between the tensor Tij and macroscopic wave propagation properties. For case A, we want to when we want to obtain X-like cross-like wave propagation, the ratio of T1 and T11 and T22 should be equal to -1. On the other hand, in case B, when absolute value of T11 is extremely greater than T22, or T22 is extremely greater than T11, the bidirectional wave propagation is obtained. So the objective functions for design of hyperbolic metamaterials for each case can be formulated like this slide. The first objective function is formulated so that the ratio of T11 and T22 tensor value equal to -1. On the other hand, in the second objective function, by reducing the absolute value of T11 or T22, we can obtain large ratio T11 or T22. And in our implementation, we use the level set based topology optimization and technique. Skip this. In this technique, structure is represented by a piecewise constant level set function. So the obtained optimal solution using this method have very clear structural boundaries. And in this method, using this scheme, the design is updated by based on the time evolution equation. Here, f prime is a topological derivative of the objective function f. And we introduce the diffusion term as shown this equation to preserve the smoothness of the level set function in the optimal configuration. So we can control the complexity of the structure using this method by controlling the value of tau in this this term. Furthermore, we use isogeometric analysis (IGA) technique for numerical calculation of the magnetic field in this research. we developed a B-spline basis function to represent position vector C. And this slide shows the typical implementation of B-spline function in isogeometric analysis. And we follow the typical way for this analysis. However, such typical implementation has a crucial problem regarding the continuity on the periodic boundaries. In standard IGA, the order of continuity on the periodic boundary is reduced to C0. And such continuity reduction is very problematic and affects the accuracy of the wave propagation analysis. So, in order to avoid such situation, we introduced an extended domain approach, EDA, and we introduced an extended domain between the two-unit cell domain. And this extended domain is a fictitious domain and not relevant to physics. However, by introducing this fictitious domain, we can deal with a periodic boundary as a C1 continuity edge. So the accuracy of analysis is enhanced by using this methodology. And let me show some example of the proposed method. In the first example, case A objective function is used. Left-hand side figure shows the initial configuration for optimization. And this is the initial unit cell structure. And gray area indicates the air domain. And brown structure represents the dielectric material. And as shown in this figure, we can observe isotropic wave propagation in other initial configuration. On the other hand, right-hand side figure shows the optimal solution obtained by the proposed method. And we can observe an isotropic cross-shaped path, cross-shaped like this, cross-shaped path of wave propagation is observed. This type of wave propagation is called hyperbolic dispersion. The second example is also the design of hyperbolic metamaterial problem for different phase shift parameter. In this case, we also observed similar wave propagation property in the obtained solution. This is the optimal solution, and this is the magnetic field having a cross-type dispersion. Okay. And the third example is a design of bidirectional propagation mode. We use this type of objective function. And this is an optimal solution and we are successfully observed the plus, in this case, plus-shaped propagation in this example. Okay, so this is a conclusion. Here is a high-order flexion homogenization method for electromagnetic wave problem is applied to derive the macroscopic material property, and we used level set-based topology optimization. Also, we use isogeometric analysis with extended domain approach. And we showed some examples having hyperbolic metamaterial and bidirectional propagation materials in the example. That is all. Thank you very much.
Thank you. Are there any questions or comments from the audience? Yes, please. Please.
Okay, I can pose a question. Thank you very much for an interesting talk. I was curious on the slide number 19, if you go one back, and actually I also looked in the paper that your band diagrams do not look like the usual ones. So for example, they are very flat at the gamma point and the X point and the M point. Is this due to the homogenization approach that is only valid in a small range around these points, or why does it not look like the normal band diagrams?
Thank you.
Hello, Ole. Hello, Ole.
Yeah.
I'm sorry, we are not sure the details of this presentation actually. So we will ask the first author to get the answer. Very sorry. This is very important question. I'll ask the first author.
Okay. Thank you.
Hello. Any question? Okay. Thank you. Let's move on to the second presentation. Okay. The second presenter is Professor Akihiro Takezawa of Waseda University. The title is Sensitivity Analysis and Lattice Density Optimization of Sequential Inherent Strength Method Used in Additive Manufacturing Process. Please start.
Thank you, Professor. Can you see my slide?
Sure.
Okay. Thank you very much. It's my great honor make a presentation about my recent work in TOP webinar. So I'm Akihiro Takezawa at Waseda University in Japan. So the background of my research is thermal distortion issue in metal additive manufacturing. I think you are all familiar with additive manufacturing technology, and you may know this issue. The part fabricated by metal additive manufacturing that deforms seriously. So of course, we cannot expect original shape, and even this issue can damage the part and device. So this is very serious. The mechanism of this deformation is very similar with the welding deformation. So the heated part try to expand, but surrounding part suppress this deformation. So the melted part keep same shape with very high temperature. So after cooling, this part try to shrink, and as a result, very strong negative strain occurs. So the different from conventional welding, in additive manufacturing, this process is repeated. So this is more serious than conventional welding. So usually this process is handled. This issue is resolved by modifying the process. For example, reducing the temperature gap between melted temperature and ambient temperature by heating the fabrication plate and materials. But I would like to resolve this issue by design optimization. To perform design optimization, we need low computational simulation method for such deformation. So in conventional welding deformation, and a traditional approximation method was proposed in 1970s in shipbuilding research field. So recently, this method was modified to additive manufacturing. The key idea of inherent strength method for additive manufacturing is the fabricated part is divided by several virtual layers, and inherent strain is applied to each layers. And moreover, to keep the shape consistency between layers, the so-called activated strain is also applied. And as a result, the higher strain are applied to the upper layers, and after cutting, the bending deformation can be simulated. So this method is very popular, and recently it's implemented in many commercial softwares. But usually this method is implemented as time transient problem. So this is actually the original inherent strain method. It doesn't have a concept of physical time. This is just a virtual approximation approach. So I reformulated such inherent strain method by using recurrence relation. So to reduce the computational cost and simplicity, like this. Oh, sorry, like this. So by using this formulation, we can derive explicit sensitivity with respect to this problem by using adjoint variable method. So this is an outline of the deformation simulation using this approach. So in this example, the fabricated part is divided by 11 layers, including the base layer on the bottom. So from step 1 to 9, each layers are generated in each step, and inherent strain and activated strains are applied. And the final shape before cutting is like this, like this. And by reducing the Liang's modulus of the bottom layer, we can perform the cutting operation of additive manufactured part. We certainly obtained a bending deformation of additive manufacturing part. So we implemented this approach using for the optimization of variable density lattice. This is a little bit easier than conventional topology optimization because we can ignore the geometrical restriction of additive manufacturing part, such as the overhang angle and gray scale problem. So we first tried the variable density lattice approach. So in variable lattice density method, we have to fix unit lattice shape. So we introduced a simple square shaped lattice having square void inside. And we also introduced the powder removing holes toward each axis. And we introduced the design variable representing the density of the lattice, and we derived the approximation function about the relationships between design variable and effective elastic tensor by using a numerical homogenization, like this. And as a material, we assumed the nickel superalloy Inconel 718 having Young's modulus and Poisson's ratio like this. So this is an optimization problem formulation of my work. I tried to minimize the deformation after cutting. So the objective function is a norm of target displacement vector, and the matrix H is just a 0-1 matrix specifying a target displacement location. And we didn't introduce any constraint. The sensitivity of this objective function is derived like this by using adjoint variable method. Adjoint equation also represented as recurrence formula. But this is a end term condition equation. We have to solve this recurrence formula to backwards like an adjoint equation of time transient problem. Let me show you the numerical example. We tried to reduce the deformation of the upper plane and the lower plane of the rectangular plate. And considering the symmetry, we only model the half of the plate. This is just a crash to the problem. And we prepared the 11 layers. And the bottom layer is handled as a plate and introduced to represent the cutting operation. And the lattices are introduced to upper 10 layers. And this domain is divided by 5 millimeter lattice. And as a result, we set 200 lattices, which is the same with the number of design variable. So inherent strain approach is just a virtual one. So we have to calibrate inherent strain value using the should use experiment. But when I developed this method, I had to use additive manufacturing machine. So I calibrated the inherent strain method by using the commercial detailed thermomechanical analysis software instead. So we obtained a reasonable inherent strain value from the detailed simulation result. So by using the obtained inherent strain value, we performed optimization. We obtained a reasonable structure after 30 iterations. The iteration is very small because we don't have we have not so many design variables in this program. So let me analyze obtained structure. We can find the arch-like structure with dense lattice. So in the inherent strain method for additive manufacturing, the higher the strain occurs on the upper layers. So to reduce stress, the lower stiffness area were prepared on upper layers like this. And basically, the bending deformation, the bending force is applied to this structure. So for suppress the bending deformation, arch-like structure was formed. And we reconstructed the variable lattice density shape from this design variable distribution like this. The left side figure is transparent view, and the right side figure is cross-sectional view. We can certainly find the arch-like distribution of dense lattice. So we validate this result by performing the analysis. This is a comparison between the optimal lattice and uniform lattice having the same volume with optimal lattice. In inherent strain method, we found about 50% reduction of displacement on both top and bottom layer. We certainly suppress bending deformation. But this is an approximation, the comparison in approximation method. So we have to validate this result in detailed simulation and should be experiment. So this is a re-analysis by the detailed thermomechanical analysis. Even in thermomechanical analysis, our optimal lattice is effective, especially in the reduction of the displacement on top surfaces. So let me conclude my talk. We proposed the recurrence relations representation of the inherent strain method for metal additive manufacturing. And by using this formulation, we derived the explicit sensitivity, and we performed a variable lattice density optimization for deformation reduction. So now the experimental verification of this approach is going. So this is the difference of this work. This is the joint research with Professor Alberto and his PhD student at University of Pittsburgh in USA. Thank you very much.
Thank you. Any question from the audience, Jung?
Yes, actually, I have a question. So, this is a very interesting research. I noticed in a simulation grid you have a resolution of 10 by 20, which indicates the computation is quite intensive. I'm curious, where do you see the chance to improve the computational efficiency?
Computational efficiency about the computational efficiency of this approach?
Yeah, so I noticed you have only 200 design variables. I guess because the computation is quite intensive. So in this approach, where is the computation spent on, and is there any chance to reduce it?
Okay. So actually, the computational cost of this approach is very low. This is just repeating the linear elastic analysis several times. So we can increase the layer more. But in that case, we are hard to analyze the result mechanically. So currently, I didn't increase the resolution so much. But in future, we can try more detailed shape.
Thanks.
Matthias, please.
Yeah, thank you. Yeah, I have a related question. Thanks for the presentation, by the way. You mentioned that in your model to simulate the printing process, you derived a recurrent relation.
Yeah.
I assume that you linearized all the physics, right? It's not nonlinear mechanics involved. We concluded that if you do that, basically there's no recurrence relation. You basically get completely separated systems of equations for each layer addition. Where in your case is the relation between the recurrent equations?
Yeah, actually I only considered the linear elastic effect in this recurrence formula because the original concept of inherent strain method is basically a linear elastic analysis. But as you said, to improve the accuracy of such simulation, that we should consider the plastic deformation. So actually the advantage of the recurrence formula is each state are completely separated, and we can introduce plastic deformation in each steps. So in future, I would like to try to include the plastic deformation effect.
Okay, thank you. But indeed, now that it is separated, I think your sensitivity analysis also becomes a lot simpler. It's not like a transient. It's all separated problems.
Yeah, right.
Okay, thanks.
Niels, you have a question?
Yes,
please.
I'm curious about, so in these inherent strain models, often you need a very large library of inherent strains for different scenarios. So for what you're showing here, are you using the same inherent strain for all points in your domain, or are you looking up in a table to see, depending on orientations and layout of the design, which inherent strain you should actually use?
Yes, certainly there are many kinds of inherent strain methods recently. So I'm hard to catch up. So what kind of inherent strain are you imagining? At least I introduced the most simplest one proposed by these authors, only considering the stack of strain and generation of new layers. So I think as you said, more the advanced inherent strain methods are proposed recently. But so my approach is the primitive one comparing this approach. Sorry, I cannot make an exact answer for your question.
Okay, yeah, but thank you very much. Of course, you have to start somewhere. Thank you very much.
Thank you.
Okay, let's move on to the next presentation. Thank you very much.
Thank
The
you very
third
much.
presenter is, hold on a second. Third presenter is, hold on. Professor John Hong Yu of Yonsei University. The title is Single Variable Based Multi-Material Structure Optimization Considering Interface Behavior. Yes, please start.
Okay, can you see my presentation file?
Yes.
Okay, let me begin my presentation. I am Chung Yu at Yonsei University in Korea, and the presentation title is Single Variable Based Multimaterial Structure Optimization, considering the interfacial behavior. And this work was performed with my graduate student Cheol Kim and Hong Kyung-sun, and also with my colleague, Professor Yong Kim at Queen's University in Canada. Okay, this is the outline of this presentation, and this presentation is based on my previous journal paper published in the Computer Method in Applied Mechanics and Engineering this year. Firstly, motivation of this research. So the most important thing of the structural design nowadays is maybe the weight reductions. So for the weight reductions, as you may see, many multi-material phases based design is applied, like this kind of body in white design of the automobiles. But for this kind of multi-material design, we have to consider the bonding method. So mostly widely used bonding method like the mechanical fasteners is not good for these ones because it is not good for the weight reduction, and it also causes the noise. And also for the welding method, some materials such as the steel and aluminum, it is very difficult to apply the welding method. So the adhesive bonding method can be applied as an alternative. And this right figure shows some of the examples for the adhesive bonding applications. But for the adhesive bonding method, we have to consider about the failure. We can consider 3 modes of failures for the adhesive bonding area. First mode is the tensile stress cases, and second and third mode is related with the shear mode cases. For the adhesive bonding cases, it is very strong for the mode 2, but it is very weak for the tensile stress cases. So we have to consider this mode 1 for the multi-material design, considering the adhesive bonding method. So here is some previous works. First one is the composite material design using the inclusion of matrix. And this method, this study is studying about the shape and location of the inclusion matrix. And second one is about the 2 material phase designs, and they consider the sliding between the boundaries. And third one is very related with my research, but this research is using the extended finite element method and the Leveson method, but it is restricted to the 2 material designs. And another one is it has to use 2 meshing net. So it is a little bit complex. So the demands for this kind of research is we may be better to use the linear solvers, and we may have to increase the number of material faces. So this figure shows you the basic concept of this design. Let's see, we have 2 face materials, red one and the green ones. For the left cases, the adhesive bonding area is under tensile stress, so it may cause some kind of failures. So we want to change it, this adhesive bonding area to write the right figures. But in this case, this new area of the adhesive bonding is under compression, so we can avoid the failure by separations. So main features of this study is we can use the linear analysis, and we are using single mesh, and 2 or more material faces is available. So let me see the design method in detail. Firstly, the topology optimization method used here is relation diffusion based topology optimizations. And it is using the relation diffusion equation as the design variable updated scheme, and it is already explained in detail by Professor Izui before. So let me just skip this part. And for the multi-phase material designs, we can consider these as 3 cases. The left case is very ordinary ones, single material design with single variables. This is widely used for the topology optimizations. For the multi-material topology optimization designs, we usually use the multi-variables. So as you may see, each variable represents each material faces. But nowadays, a single variable based multi-material design is used. But in this case, as you may see, with only single variables, but by just separating or classifying the density values for each material faces, we can use only one single variables. But in this case, we have to use a little bit complex mathematical formulations to realize this graph. And also there is some numerical instability during the design process, right, in the sensitivity analysis process. So in our method, we are applying the 2 functions, psi and psi. Psi function is used to derive the surrounding intermediate density variable to the target values like these ones. Here are 5 target material faces here, including the void part. And this psi function is just deriving the density, the design variable to the target values. And the second function is used for the sensitivity analysis, because at this, by applying these functions, the sensitivity value at the target value becomes 0. So it may be useful for increasing the stability during the sensitivity analysis. And now let's begin for the fundamental concept of this process. We are applying the interface tension energy density concept here. Here is the J2 function is applied to the another objective functions. So this function is just the strain energy, but this function has the value more than 0 only in tension cases. For the compression cases, it becomes 0. It can be realized by just considering the interfacial layers, the normal directions related with the tension and the strain directions. So it can have the positive values only when the values of the strain energy becomes positive values. So for the optimization problems, as you may see, we combining to the ordinary compliance objective functions together with the ITD functions. So all by combining these 2 objective functions, we can realize we can avoid the separation in the adhesive bonding area. But in this ITD formulations, there is some Dirac delta function formulation appears. So it causes the sensitivity instability like these ones. So to avoid these instabilities, we use the Helmholtz filtering for the sensitivity calculations like these ones. So we can remove this flickering effect in the sensitivity analysis process. And as you may see, this one is just before filtering, and after applying the filtering process, that we can avoid the sensitivity fluctuations. And this is the overall formulations with the objective functions and the volume constraint. And this constraint is for the constraint for each composition part. And this one is explaining the sensitivity and the optimization process. And this flow chart is just to show you the overall process for this design process. Now let me see the numerical examples here. First example is the cantilever beam. The force is applied here. For the perfect bonding case, assuming cases, As you may see, we are considering three-phase materials, including the void part, and this part is under tension. So if this part is bonded with the additive bonding, it may causes some separations. So by applying the bonding behavior using the ITED concept, the structural design is changed like this ones, and the bonding area here and here, it is under compression stress. So it is free from the separations. And along these lines, we can see the material changes. The red part is material phase 1, and the green part is material phase 2, and the blue one is the void part. And right figures shows you the convergence graph of the objective functions, and the bottom graph shows you the material property, each material's volume fraction change, and also total volume fraction changes. And another example is the half maybe been designed like this ones. So perfect bonding cases, as you may see also some the adhesiving part is under tensile stress. But just applying the proposed method, we can see the bonding area is under compressions. And we can apply this method for the 4-phase material, 5-phase material also. So it is a little bit complex, but anyhow, each color represented each materials, right? The material phase 1 to 3, including the voids, right? This or including the void, right? These ones. And the perfect bonding cases, this part is, as you may see, under tension. But by just applying the ITD method, we can see the boundary area is only under compressions. And 5 phases cases also you can see similar results like this ones. And another one is it is not so much related with this research topic anyhow. By applying the multimaterial designs, we can see a kind of skin layers like these ones. So this is a little bit small and very thin layer, but anyhow it is composed of the different material phases. So it may be better to avoid this kind of skin layers. So to avoid the skin layer phenomena, we apply the heaviside projections, 2 steps. First step is after applying the first step, we can see the change here, and the second step, we can see the change at this part. So the heaviside projection effect projection is effective to reduce the boundary layer material generations. So the conclusion is we are applying the ITD concept here to avoid the tensile stress area is not included in the adhesive bonding area. And the effect of Helmholtz filtering may be explained here, and you can see the numerical examples like right figures. So that's my presentations. Thank you for your listening.
Thank you very much. Is there any question? Oh, yes, News, please.
Yes, I do have a question. So thank you for a very nice presentation. So I'm kind of curious about this single field versus multi-field representations. You actually kind of answered half of it, I think, on the slide 24, I think, was it? Or no, 24 here. Yeah, one back. So I guess the stacking sequence of your materials will be predetermined the interfaces, right? You will always have material 1, then 2, and then void. So have you tried switching those around just to see, does it have an influence on the optimized design if you interchange material 1 and material 2?
Well, we haven't experienced such a kind of cases, but what I understand your question is you may see the phase changes during the design process, right?
Yes.
But it does not happen so much in our study cases.
Okay.
But the important thing is, I think the how to define the material faces like this one. So you can see so many ways to define the material faces, right? The Professor Saito's work and other guys' works here. But problem is, this part is, some way it is a little bit flat and some kind it is abruptly changed. But such a kind of abrupt change causes the instabilities during the sensitivity analysis usually. So I think the best way to avoid such a kind of sensitivity instability also maybe for the phase change during the design process, I think the smooth representation but effective for representing each material mathematical formulation is important, I think.
Okay. Yes. Thank you very much.
I don't know. Yeah. Thank you.
Any other question? Any question? Any other question? No? Okay, thank you very much.
Okay, thank you.
Let's move on the next presentation. The first presenter is hold on a second. Dr. Martin Pierre-Schmidt of R&D Simulator. The title is Structural Topology Optimization with Smoothly Varying Fiber Orientation. Please start.
Thank you. So thank you for the invitation, and also thank you for to all the organizers for setting up this whole webinar. So in this presentation, I'll be talking about work that was published in the SMO journal this year. And basically, it will be all about setting up optimization, topology optimization, so that we can optimize both density and orientation of some anisotropic material. So I don't think we need to go over the reasons why this is a useful capability, but more specifically here, we'll be setting this up as an optimization problem because we will be looking at multi-load case scenarios, meaning that we can't use the local stress tensor in those type of conditions. So first of all, we need to model the material, and we'll be using orthotropic constitutive law, which is given here on the right in its stiffness form, which is defined by 9 distinct parameters, the Yang, Poisson, and shear coefficients. And if we are looking at fibers orientation, then we can reduce that to transverse isotropic material, which is just defined by 6 coefficients. Then because we want to actually do optimization on those orientation, we also need to define the variables. So for that, what we have is the constitutive law here, C, and we will introduce 2 transformation matrices, T alpha and T theta, which will be basically acting as rotation on the constitutive law. And from there, we can then define the stiffness matrix for each element as a function of the density, as it usually does in topology optimization, penalized by a factor, and also as a function of the 2 parameters alpha and theta for each element. Then again, we want to do optimization, so we need the derivatives of the objective function, which will be the compliance. So that means that first step is a joint analysis as usual, and the rest is getting the partial derivatives of the compliance with respect to our additional design variables alpha and theta, and we do this as usual with the chain rule. So the details are given here. And so in the paper, there is a whole section about the non-convexity of this problem, but here for conciseness, let's just accept that this is a very much non-convex optimization problem, meaning that using the pure gradient descent update rule for those design variables is simply not a valid option. So instead, what we'll be using is a hybrid scheme that uses 2 parts. Basically, you've got one part which is inspired from stochastic optimization, inspired from simulated annealing, and then there is a gradient descent component. So the update rule looks like this, where we have the gradient term here, and we have this term right there, a normalized term, which is the simulated annealing energy term. And it will be responsible for the size of the steps that we'll be taking as we optimize the design variables alpha and theta. So the gradient gives us the direction, and the simulated annealing energy term gives us the size of those steps. And we have move limits that will progressively tighten as the optimization progresses, so that we initially move quickly, so that we basically shake things up, and then as the design starts to converge, we tighten those bounds to converge to the final solution. We also, again, as it's pretty common in topology optimization, we also need to put some form of length scale control on those material orientation variables, because if we do not, then we may end up with a situation where the design field basically has high frequency variation in the orientations. And this is what you can see there. So in order to avoid those, we apply a filtering, which is done in vector space, because it's just more convenient than in the angles. And by doing this filtering, the optimization then converges to a much better solution with smooth orientations and a better defined density field as well. So a side effect of this filtering is that it also allows to avoid a bunch of nasty local minima in the orientations, and it does reduce the final compliance by a significant amount. So just to check mesh independency, here we have an experiment where we have a single scenario, and we increase the resolution of the mesh without increasing the filter radius in these two examples here. And we see that as the resolution increased, but not the filter radii, we basically have sharper turns in the material orientations. Whereas if you do the same experiments on the right, but now we increase the resolution and also the filter radius, then we see that the orientation field maintains basically the same curvature along the edges of the design. So now that we have all these components, we can formulate the global optimization formulation, which is a so optimization of three design variable fields, the densities and the two angles in 3D. We have a softmax aggregation to handle multiple load cases, and we are using here the global mass constraint, and we have the hybrid optimization scheme for the design variables alpha and theta, as well as the regularization scheme. So that's our whole workflow. And using this, we run a bunch of experiments. So the first one is basically trying to run on high resolution meshes and multiple load cases. So we have a simple design space, which is a cube, and each of the 8 corners of this cube are fully clamped. And we have three different tests with different resolutions. So we have a 64 cubed, 128 cubed, and a 160 cubed voxel resolution. And we, for each of those, we generate randomly 5, 5, and 8 load cases inside this design space. So that gives us, for the largest resolution problem, about 12 million design variables to optimize, because we have about 4 million voxels, each having a density and 2 angle orientations. And so if we look at the actual result as it's being optimized, you can see, so in the first iteration, it basically looks like a blue fuzzy sheet type thing, where this is because we initialize the density field as a uniform value, and the orientation field is initialized randomly in 3D. So that gives us this starting position, and then after about 10 iteration, the compliance drops very sharply. And after these iterations, we can see that there is some oscillations in the compliances for the 8 load cases. And this is due to the simulated annealing part of the update scheme that is basically shaking things up so that the fiber orientations settle in the best local minimum that they can find. And in most cases, using this approach, after 40 to 60 iteration, the design space converge with all the design variable fields, staying fairly stable. And after convergence, we obtain a design space which contains a fairly well-defined density field with nice and sharp solid and void regions. And in these solid regions, we have smoothly varying fiber orientations inside the solid. So now we look at another scenario, which is the GE jet engine design bracket. So it is a scenario with 4 distinct load cases. We have 3 static loads and 1 torsional load here, and the design space is restricted to work inside this orange part right there. So here on the right, you can see in blue the density field, the isosurface of the density field after convergence. And we optimize this using a min-max formulation, which explains why you have the compliances for each load case crossing over right there. And you also notice that it drops sharply in around 10 iterations, and then you can see those same oscillations due to the simulated annealing part of the optimization. And here we visualize the material orientation field, and it is color-coded with the angular velocity of those streamlines. And the reason why we use this visualization is because it allows us to very quickly spot the regions with the sharpest turns. And this is so that even in very complicated shapes, we can still quickly see if in the sharpest turns, the streamlines are still fairly smooth and acceptable for our purpose. So here we're looking at another scenario based on the Juno space probe, where we're optimizing the support frame for the high-gain antenna, and it is made with a multiple load case scenario based on the launch peak G-forces. So we compare 2 different designs, one using just a straight up isotropic material, so basically standard topology optimization, standard SIMP. And on the right, we have, with the approach presented here, using oriented orthotropic materials. And the main takeaway is that with isotropic materials, you can see more cross members in the design, and you can also see that whenever the structural members fork out, they tend to have a larger angle in the fork, whereas with the oriented orthotropic materials, you don't have those cross members, and the structural members tend to split with the shallower angles. And this is this is expected because with shallower angles, you have less divergence in the material orientation field, which means that you benefit more from your fiber orientations. Then we look at another scenario, and this scenario is basically made to create a very challenging task with a very complex, geometrically very complex structure, so that if the optimization works well, then we can more or less open the bottle of champagne. So the idea here is to use the porosity constraint or local volume constraint to enforce a very very porous and very intricate structure. We can see here on the design the density field on the right. We also have 3 different load cases aggregated with a softmax function, and we have obviously the design variable fields alpha and theta, where actually this is in 2D, so we don't have theta, so we're just optimizing for alpha. And you can see on the right the material orientation field for this specific solution. And we notice that even though this structure has many crossing members, and in 2D you cannot have 2 crossing members without having orientation singularities, but even though this is a fairly challenging problem, the material orientation field still settles into a fairly smooth and well-defined orientation field. So this is a satisfying outcome. And finally, we look at a small extension of this approach, where we introduce yet another design variable here, tau. And this design variable will basically be acting as a ratio of orthotropy in the optimization problem. So what we do is we define the constitutive material as an interpolation between an orthotropic and isotropic material. And this coefficient tau is basically the ratio between those two. And this allows us to delegate to the optimization scheme the choice between isotropic and orthotropic material. Notice we also put a penalization term here so that we avoid intermediate choices, basically. So again, we need the gradients for this design variable with respect to the compliance, and this is done achieved using the chain rule, and you have the missing term right there. And if we look at the design, we then have the density field that gives us the overall shape. We have the material orientation field that gives us the material orientations inside that shape. And we have the field, the tau field, the ratio of orthotropy, that tells us that basically in those hubs, it's more efficient to use isotropic materials here to connect those long and slender beams. And in those beams, the material orientations are aligned along, the fibers are aligned along the length of those beams. So we can do the same in 3D. And again, we observe this same kind of result where we have the design having isotropic hubs connected by long and slender orthotropic beams with the fiber orientations aligned along the length of this beam. So to conclude, in this presentation, we've introduced a formulation to define a varying varying orientation of orthotropic material within the optimization workflow. And we've proposed an optimization scheme that can handle the non-convexity of this optimization problem. Then we've shown that it does work on multiple load case scenarios and also with additional constraints, like, for example, the porosity constraint. I did not show the compliant mechanism one, but maybe I can if we have the time. And then we've quickly extended this approach to have another design variable that basically allows us to delegate the choice of using isotropic or orthotropic materials in the optimization. Thank you very much.
Thank you very much. Okay. Are there any question? Yes, please, Niels. Niels, please.
Yes, I do have a question. So first, just a small note. If you go to slide 11, this is just a curiosity. Maybe this is due to the simulating annealing here. The slide, yeah, here. So after iteration, 25, all the compliances seems to be going up. Is this because you have a projection in your scheme that you didn't tell about, or why is that happening?
That's actually a very good point I forgot to bring up. So basically, this is also something we notice in most other optimization cases, even though it's not necessarily as visible. But basically, when you fall to this this point around like iteration 25, 30, you have the lowest compliances, but the design, the material orientations are not necessarily as smooth as they could be. And so after that, the move limits in the optimization are tighter, and the filtering is still acting to basically smoothen the orientation field. So that means that after this situation, the compliance may be lower, but the orientation field is not necessarily as smooth as you might want it to be. And this is why it increases slightly, and then it settles back again around iteration 50 or somewhere like that.
Okay, I think I need to read the paper. I'm still not sure where you put the constraint on the smoothness. I thought you put that into like the
it's a
update scheme.
Yeah, it's a filtering in the on the material orientations, but this filtering is basically still acting after iteration 30, whereas the move limits on the optimization in the update scheme are tighter. So basically the filtering takes over at that point and makes sure that the final design is smooth.
Okay, thank you. And then my actual question. So I'm no experimentalist or guy who produces anything, but I would assume these are pretty hard to build.
Oh, of course. And in fact, one of the reason why we opted with this approach of having still having the density field and then adding other fields to define different properties is that we can easily use the same code that does just traditional isotropic. And if we want to do optimization in a 2D plate with the material, with fiber orientations, then this is potentially manufacturable, and this can be done by just adding one of the design variable fields. And if we want to unlock and do full 3D, then it probably isn't quite manufacturable, at least not with continuous fiber with today's technology. However, one other option is to actually interpret this material orientation field not as continuous fibers, but instead as microstructure, oriented microstructures, which in this case might be manufacturable.
Yeah, I was more thinking like you already showed that you can visualize the curvature, so you could constrain that and then ensure that you wouldn't have too dramatic changes in the fiber layout. Mm-hmm. I guess that should be doable as well. But thank you very much. Nice presentation and awesome pictures.
Or you have a question?
Yes, I also liked it very much, and I think the single orientation in your 3D structures looks really convincing. But an obvious question is that often, or almost always, when you do composite structures, you would have the possibility to have various layer directions and put up layers. So have you thought about whether this scheme could be sort of extended to include multiple directions?
Yeah, so obviously if we are in like in full 3D and we want to actually use an orthotropic material with three different stiffnesses for the three principal directions, then we would need to actually model the three angles to actually have the twist around the main directions, which we don't have to do if we just focus on fibers. And then if you want to actually go towards proper anisotropic materials, then it probably would need to change a fair amount the actual choice of obviously the constitutive law, but also the design variables that we want to use, because then we want to make sure that they don't necessarily the different orientations don't necessarily overlap, because then it becomes very challenging to actually see if it's just one very stiff directions or multiple that overlap. So it becomes a kind of a mess to track.
Mm-hmm. Thank you.
Okay, any other question from the audience?
I have a question,
yes,
if I can jump on. So it's also regarding the fiber orientation and the way you get it. So you say that you're using a simulated annealing method for the orientation of the fibers. And this might just be me who's a bit not that familiar with these methods, but as I understand it, they're quite sensitive to parameter changes and to the temperature changing and how you reduce the temperature in your simulated annealing. Do you have any comments as to, in general, if you want to use simulated annealing for topology optimization, how to handle those parameters?
Yeah, so so first, the simulated annealing is actually more of a figure of speech in the sense that we are kind of having this idea of cooling down the material, basically letting the fibers settle in the stable orientation, but we still follow the gradients to optimize. And this is why we can optimize a problem with something like 12 million design variables without actually having to run more than a few, like 100 iterations or whatever. Obviously, if we want to actually go for a completely stochastic optimization, then this is not, I don't know how you would want to do that, honestly. Gradient is the way to go if you can have them.
Okay, so it's just that you're tightening your constraints or your filter.
Yeah, and we basically have this like shaking things up in the beginning, but it's still following the gradients.
Okay, okay. I think also, yeah, thank you very much. That is a good answer.
Okay, any other question? Comment?
Okay, can I ask a question? Okay.
Yes.
So you are okay. So you are optimizing fiber orientation of anisotropic materials for compliance minimization problems. So have you considered to apply a method directly for other problems such as vibration problems like organ frequency maximization?
Well, so the reason why we wanted to also have this like orientation field as basically a fairly explicit definition in the optimization workflow is that it could also, if we can model another problem, and so we didn't specifically think about vibration or anything like that, but we did think about thermal diffusion, because then it's fairly easy to have an isotropic thermal diffusion, and we can also get the gradients fairly easily. And so indeed it does work. I don't have any examples there, but basically it does work. You can define the anisotropic thermal diffusion and then optimize with respect to thermal compliance, for example.
Okay, thank you.
Okay. Any other question? Thank you very much. Let's move on to the final presentation. The presenter is Professor Leonard, PhD. I'm sorry for my bad pronunciation. Professor Leonard, PhD, is it correct? Of University
almost
of University of São Paulo. The title is Topology Optimization of Binary Structures under Design-Dependent Hood Structure Interaction Laws. Please start.
Yeah, thank you, Professor Nishiwaki, for the nice introduction. Yeah, my name is Renato Picelli. I speak out from São Paulo city. It's a pleasure to be here. I'm delighted with it. And thank you to the organizers as well. I want to share our last piece of research. The core of my message today is about fluid structure interaction in topology optimization. That's a topic I've been working a few years and I'm very interested in it. I'm also talking about a recently developed method called TOBS. We developed this method 2 years ago, and our new recipe for FSI design with results and conclusions. Okay. Yeah, arguably, this community has been developed very great methods of topology optimization to a very wide range of interesting problems. But today, I want to grab your attention to multiphysics problems, which in my view are underexplored and very challenging, of course, because of the challenges they pose. Problems like hydrostatic fluid pressure in structural design, submerged structures, right? Thermoelastic design, acoustics, fluid flow optimization, etc. And the topic of today, that is fluid structure interaction, that mainly includes, comprises a viscous fluid flow flowing around elastic structure, like this 3D example here. Fluid is getting in the inlet, blue inlet here, getting out of the orange outlet here and interacting with this elastic gray wall. I will come back to this example in the end. The objectives of my of our work then is to carry out topology optimization of FSI problems, use the TOBS approach we developed years ago. And this work is specifically to create an algorithm to decouple analysis optimization grid using these two items, aiming to, as a motivation, to extend to other physics design, not only FSI, but FSI is our first problem to tackle. As you can see here, fluid structure interaction problem can be divided in two approaches. The first one is dry optimization. If you have a fluid flowing around the structure here in a design domain, if you keep the fluid structure interfaces fixed, you say no, they cannot be removed or they cannot change. You only optimize for the dry bits of the structure, so the internal holes. But if you have your structure under the water and if you allow it to change the fluid structure interaction, the fluid structure interfaces, you have what we can classify as wet optimization, and that's the problem we are looking at. The loads change accordingly to your interfaces, so therefore you have a design-dependent loading problem. Okay. So that's the first actually scientific and technological challenge, is how to do with, it's very nice move here, is how to deal with the FSI design-dependent loads, how to impose the equilibrium conditions properly, and which phenomenon we want to look at, because there are several types of interaction between a fluid flow structure deformation, can be small displacements, large displacements, etc., laminar flow or not. Okay, and available methods in the literature are working on that. So I brought here 4 of them. SIMP has been applied here, LSM, level set, of course, BSO, and our work on TOBS. Okay, so mainly the differences are in how to deal with design variables and how to tackle these two conditions here. Okay, so like density, overlapping domains, level set shapes, and binary variables here. Okay, and our topic from today is the one that was listed in the lineup of the agenda of the top webinar from today. This was the paper we published in SMO this year. We are using the TOBS method, the optimization method, as a standard, as we proposed it 2 years ago. The focus of this paper is how to deal with FSI design using this standard approach. The TOBS, between some other characteristics, is based on binary design variables. In my view, in our opinion, this problem is naturally binary, because we want to have a clear distinction between solid and fluid, so that what binary design variables might offer. Also, we can have less or no effects at all from the material interpolation now that we are using only solid and void or solid and fluid. And we can easily aggregate this with commercial software and simulate the complex FEA here using separate domains. All right. So, okay, the problem we are looking today is to minimize compliance subject to a single or multiple volume constraints and binary variables, okay? So a fluid flows in a channel around the structure, interacting with the structure, deforming, loading the structure, and the structure deforms, okay? The fluid flow is governed by the incompressible Navier-Stokes equations. We are looking to low Reynolds number, okay? And so far we are doing a linear elasticity. I understand that the FSI problem can go easily further beyond this complexity of this problem, but we have to start from somewhere, and we are starting with the linear elasticity. So it's small displacements, okay? There's no big changes, large changes in this deformation. Okay, the TOBS approach, which stands for topology optimization of binary structures, as we called it 2 years ago. The standard form of this method uses 4 numerical ingredients very well known in our community. First, sequential approximate problems. So we are solving the approximate linearized problem, okay? We have 2 moving limits here. First is epsilon, that we relax the constraints, okay? So we control the steps and how the constraints move towards its prescribed value G bar, and it can address multiple constraints, okay? And the second move limit is beta, which we control the amount of changes in the design variable, so we keep our truncation error due to linearization low, okay? We are using binary design variables, but actually we are solving here for delta x and not only x, not just x, okay? If we keep delta x binary, our original design variables x, vector of x, will be binary, okay? We use sensitivity filtering that's more suitable for binary variables and integer linear programming. We do recommend to use the branch and bound algorithm in Cplex so far, at least, by IBM. You might ask me if this is slow or not, but this is not as slow according to our observation. Of course, this is slower than MMA and other solvers for density-based, but the bottleneck is still the FEA simulation, okay? We published an educational paper this year that you can have more details of this method. Okay, but that is the standard form we use in TOBS. The paper from today is aims to use this TOBS module, okay, and a separate module with your FEA. So we are trying to decouple the optimization grid and the FEA, okay. For FEA we use console, and we communicate between them by, we have a set of binary variables. We construct a CAD model in console. We extract sensitivities in some FEA grid points, coincidentally with the optimization grid. We come back to the solver and we solve to the ILP, right? And we solve for a new set of binary design variables, and we go back. That's how we communicate between both modules. We use automatic differentiation for sensitivities, and geometry trimming, at least we're calling it geometry trimming, to build the CAD model. Maybe it's easier or it's clear here. We have our TOBS model. Okay, we have that the wall problem there. I said we have a binary solution. We trim the design domain and we build a CAD file with our FEA software. We leave the software to mesh the file as it wishes. This might be advantages in terms of simulation accuracy. Okay, we solve the forward problem, compute sensitivities, and iterate. These might look similar to some algorithms used by level set methods as well, but to the best of our knowledge, this is the first time we combine such thing with binary solver, okay, with a binary based topology optimization method. Okay, so our first problem is the wall problem. We have a fluid flowing from the left to the right here. It hits the wall deforms. Of course, we are considering small displacements here. We are minimizing compliance, subject to a volume constraint of 35% of this gray area here behind the wall. The wall is non-designable. Okay, the black thick wall here is non-designable. we use water, fictitious material property for the solid, these two parameters. You can see here, starting from iteration 0 to 111, how material is being removed and the fluid occupies the region where originally was designed, the design domain. Okay, this is for Reynolds, very low Reynolds number. Okay, this is for Reynolds 10, and this is for Reynolds 100. We are seeing here the velocity field of the fluid, but we can clearly here identify how the structure looks like. Okay, but here is the trimmed geometry. This is the CAD file I extracted from the software, and we have observed that for very low Reynolds number, the outer shapes of the structure were more like convex, while for higher low Reynolds number are more concave. And this is because, to my observation is, if I still have an invitation, please look here. This is the pressure field of the fluid flow, okay? For very low Reynolds number, we have a positive pressure on both sides, so creating a crushing loads in the structure. For higher Reynolds number, so higher velocities, we have here light gray, light blue, so it's negative pressure. We have pulling loads here. So it gets to form these inverted arch or concave shapes here, okay? So that's what, and that actually depends on your reference pressure, of course. The paper discusses that in detail. Okay, so our second example is a fluid channel as well, but with 4 walls and 4 volume constraint, 1 volume constraint per wall. This is easily carried out by the solver as well, without changing anything, because the formulation of the problem is already for multiple constraints, okay? We have observed here that's the structure, the final optimized structure. We have convex shapes at the beginning, and in the end we have negative pressure here, and we have convex, concave shapes here. Okay, this is the fluid velocity, or CAD model, pressure, fluid velocity. All right. And then the 3D example again, this is a 3D extension of the wall example. By the time we published the paper, we didn't have this implementation. It's just the same implementation, but more efficiently. And now we are able to do the 3D wall. But this is for very low Reynolds number as well. It's basically the same problem, but just 3D. One thing that is nice is that it's easily extendable to 3D because, just trim geometries and according to your holes and go on, okay? This is the wall, again, minimizing compliance, subject to a volume constraint of 35%. And fluid water, this is how the structure looks like in the end. This is the fluid velocity, the streamline actually of it. You can see here is the very low Reynolds number. And yeah, the fluid flowing around the structure, okay? And as a conclusion, I bring that compliance minimization of structures under fluid structure interaction loads was successfully solved. The TOBS approach in the standard form is suitable for the problem. It's at least a competitive candidate because of its binary design variables and mathematical programming, okay? And we bring in this paper a new recipe of decoupling analysis and simulation in the context of binary design variables and FSI, okay? Future work should increase the complexity of the FSI simulation or maybe extend this to other physics, okay? These are the references I mentioned during the presentation. Thank you all for listening to me. That's very nice to have the opportunity to share this research. I publish my I also share my research in this also social media. Let's follow each other on my Twitter, okay? And thank you very much. This is my email. I'm glad to answer questions now if you have it. Thank you.
Thank you very much. Are there any questions, comments?
I have a question.
Yes, please.
Okay, thank you very much for your presentation. In the slide 11 and 12, you showed us that how you are going from your optimization to console and you are coming back. I didn't get exactly about the sensitivity, how you are calculating the sensitivity. That is in the console part. Could you explain that part?
Yeah. So maybe here in the, everything apart from solving the optimization problem is done in the commercial software. So sensitivities as well. This is actually a crucial point for the method, all right? We create a point, a grid of points here that are coincidentally with our optimization grid. So we can extract the sensitivities at the points. So that's maybe the unusual part of this approach, that we are computing the sensitivity at a point, not an element. That's why I'm saying we are decoupling analysis, so the elements, the finite elements, and the optimization variables, the design variables. So we have a grid of points here upon this mesh, and we extract the sensitivities at the points. I carried out fine differences, creating nodes right at those points, and it worked out. So at least at this point, I'm confident that I have something at least.
Okay, and in your paper, do you have more data? We could read that part, because for me, it is unclear how you are going from the points to the nodes and how you are coupling this solver and your finite elements software.
Yeah, I try to explain in details, even with the COMSOL's functions and how to use it. We use the simple model to help the automatic differentiation, okay? And yeah, we have sensitivity field like this, and we interpolate the sensitivity field that I think the COMSOL interpolates the sensitivity field at those points and extract, we set then the design variables with those sensitivities. Okay. And so, okay, thanks.
Thank you.
Any other question? Niels, do you have a question?
Yes, sorry, it was along the same line. So I guess this works very well due to a one-way coupling. So how would you, again, speaking of the sensitivities, if it was a two-way coupled problem, speaking again of large deformations, would this segregated analysis still be possible? Or how would you think about transferring information between the two different solvers packages?
Yeah, maybe it's another great question. Thanks. Maybe that's the key point to extending this method, right, to large displacements. We have the material framework and the spatial framework. We still have, okay, we will have a large displacement, but we will still have the correspondent material coordinates, and we would be still able to compute sensitivity at points. So in the end, after you solve the large displacements field, your grid, FEA grid points will be deformed as well, accordingly to your elasticity deformation. Yeah, it's possible. I'm almost sure. Yeah.
Yeah, I agree.
I might bring it something like this soon. Maybe in WCSM.
I would just assume that it would become quite expensive, because you would have to do a fixed point iteration between the two solvers, also for the linear adjoint in the end.
I think it's cheap in terms. It's relatively cheap for the complexity of the problem, because of this. Because we have a very it's not a very refined mesh. It's only refined where it's more important. That is the FSI interfaces, right? So of course, if I have the same discretization of TOBS here, that would be quite expensive. So I'm saying that in my view, one of the advantage of the method is to be relatively cheap for the complexity of the physical problem, because we have a considerably coarse mesh here.
Okay, thank you. Looking forward to the large deformation results coming out soon.
Yeah, well, me too. So thanks for the two questions. Very nice, very nice.
Okay, are there any other question? Comments?
Yeah, probably because it's quite late for our Asian colleagues.
Yeah, I think the time.
Thank you very much. So, John,
no, thank you very much. Thank you.
Thank you everyone for joining us today, and thank you Professor Shinji for organizing this session.
Also, thank you very much, John. Also, thank you very much for all audience for your cooperation.
Thank you.
Thank you.
A short announcement. So this is the last seminar before the new year. In the new year, we will start with two thematic sessions. The first one is on data-driven approaches, organized by Professor Wei Chen from Northwestern University. And the second one in February, there will be a session on fluid and thermal transport problems, which represents one of the underdevelopment problems in the community. And I wish you a nice holiday season and see you next year.
Thank you very much.
Bye bye. See you
Bye
next
bye.
time.
Bye.
See you next week, next year.